Hello and welcome back to my Physics Online Video Lecture Supplement series. Today's video, I am returning to the set of lectures 7, which are on energy and its conservation, and specifically I wanted to look at the second part of this set of lectures, which is about two types of potential energy. So in the previous part of this set of lectures, I talked about work and the work energy theorem, and I mentioned that potential energy was the energy that's associated with the position of an object. It's the potential of some force to do some work upon an object, in other words. And there's several types of potential energy. If we strictly define it as potential for a force to do work on an object, then there's really going to be about four broad types of potential energy that we will encounter in this introductory physics course between this semester and next. And as it turns out, two of these are types that we're going to look at more this semester, and two are the types that we'll look at more next semester. So as far as this semester goes, the two types of potential energy that we're more interested in are going to be energy that's stored by an object due to its position in a gravitational field, and energy that's stored by a spring when it's either compressed or stretched away from equilibrium. You could think of this maybe as elastic potential energy. It could also be applied, for example, to a stretched rubber band. And the other types of potential energy that we'll look at more next semester are going to be energy that's stored by charges in the presence of an electric field. We'll especially look at that in the context of capacitors. And then energy which is stored in a magnetic field. So again, today we're going to look at gravitational potential energy and elastic potential energy, or potential energy for a spring. Okay, so let's start with gravity. So gravitational potential energy is the potential for gravity to do work on an object. And as long as you are near the surface of a planet, the gravitational field is pretty constant. That's another way of saying that the force of gravity which acts on a given object is constant as long as the object's mass is not changing. So of course, even near the surface of the Earth, you can have a thing which has a changing mass. For example, a raindrop, as it falls, may collect more water and get larger and larger and larger, and therefore there's more gravitational force on the raindrop. But by and large, objects that are near the Earth's surface tend to have not only the same mass, but also the same weight. And that means that the force of gravity tends to be more or less constant when acting upon them. Okay, and that means that if we want to look at the work that's done by gravity when an object is either lifted or when it's falling, that is again force times the distance that the object moves that's parallel to gravity. So in other words, force times the y displacement if y is the up direction. Or you could just think of it as force times displacement times cosine of theta, but again, theta is going to be the angle between the actual displacement and the upward direction, or the vertical direction. So that means that the work done by gravity, this W again is work, not weight, is going to be mg times change in height. Mass of the object times the free fall acceleration times the change in the object's height. And so oftentimes we associate the potential energy due to gravity with the basic amount of work that gravity can do if the object is released. And so that's going to look like the mass of the object times the free fall acceleration times the height of the object. And so this height of the object is sort of the key changing parameter in this case. And so you see a little diagram over here of basically a cuckoo clock. Essentially what happens is that this little weight is lifted up initially. For example, you basically pull this little cord downward, you apply some force to it, it lifts the weight upward. That means that you do some amount of work against gravity, and that amount of work is going to be m times g times the change in height. So we'll define the lowest height of this thing, in this case, as h equals 0. And so then the potential energy is whatever height above that lowest height you're at. And so then as the cuckoo clock runs, basically this weight is able to fall a little bit. And so that means that gravity works against this weight, and that ultimately ends up sort of providing some energy for the cuckoo clock to run. And that energy should be m times g times h. Before I move on to changes in potential energy, it's worth making one quick note here, which is that I sort of tacitly defined a reference height. In this case, it was the lowest height that the weight was going to obtain in this motion. It turns out that you need to define some reference height in order to use this equation, E equals mgh. And that reference height can be whatever location you want to use. It might be maybe you're inside of a building, as is the case of this guy who's carrying this television set up several flights of stairs. And so you could choose different possible reference heights for this television. For example, there is the ground outside. So this is, this could be your height equals 0. And so then your current height would be this. You might choose the floor below to be your height equals 0, in which case you'd use as your height this value. You might choose the distance above the stair that this guy is lifting it to be your height, in which case your initial height is this value. And it turns out that as long as you've picked some particular reference height, once you've made that choice, as long as you stick with that choice, it doesn't matter where you pick the reference height to be. Now, one implication of this, of course, is that you can get the potential energy due to gravity to be some negative number. So you use mgh. Well, if you chose this to be your reference height and this guy drops the television and it falls down the stairs and lands down here, you'd have a negative height in this reference. And so it's possible for EG to be less than 0. So that's okay. Just keep in mind what you've picked as your reference height. And actually in the lab in particular, it is convenient oftentimes to pick the height equals 0 to be some distance other than the distance from object to ground outside. For example, maybe you're doing a lab inside a classroom on the 3rd floor or 4th floor even. So maybe you have a table that's set up here, and you're trying to drop an object onto the table. So you've got this object, you're going to be dropping it onto the table. Odds are that the best option is going to be to measure everything from this point as your height equals 0 point, your reference point. Even though this table is above the floor and this object can in fact fall to the floor, and even though this floor is in fact above the ground and this object could hypothetically fall to the ground. So your reference position usually just gets chosen as a matter of convenience. Therefore, going back to this cuckoo clock, I chose the reference point as a matter of convenience to be the lowest point that this weight is going to go with respect to the cuckoo clock, even though the cuckoo clock may be on the wall, even though the floor may be down here somewhere, and even though this cuckoo clock may be in an upstairs bedroom somewhere. So when we say that the energy due to gravity is mass times free fall acceleration times height, we really mean that this height is with respect to some reference height. And again, when you look at work done by gravity, it's m times g times delta h, and this is the key to why it doesn't matter where you pick your reference height at, because we're usually going to use this in the context of a problem in which the height has actually changed. And so the change in height is the same whether you took the reference height to be here at the floor or here at the ground outside or here at the bottom of the motion. This right here is still the same change in height. And so therefore, usually what we're interested in is that you do work against gravity and it's equal to the change in the gravitational potential energy plus ultimately the change in any other potential energies and the change in kinetic energy and so on. All right, so much for the case where you have a constant force of gravity. However, gravity is not actually a constant force everywhere. The constant gravity assumption is actually valid if you are changing height very little with respect to the size of your main attractor. The main attractor basically is whatever body you happen to be on that is providing the main gravitational pull. So, for example, the Earth. So, here is the Earth. And usually we do our experiments pretty near the surface of the Earth. And therefore, these changes in height are relatively small compared to the radius of the Earth. So this is the basic condition then. So the question is, what happens if you go farther away from the Earth? Obviously, this picture is not standing on the Earth's surface, but rather standing somewhere near the Moon's surface. So for one thing, the gravitational main attractor is going to be the Moon. Okay, fine. So we use the free fall acceleration on the Moon, which is about 1/6 that of the Earth. But hypothetically, what if you were this distance away from the Earth, but in the other direction? In other words, not on the Moon, but somewhere over here. Well, in that case, you have to start using Newton's universal law for gravitation. And you'll recall that Newton's universal law for gravitation, or Newton's law of universal gravitation, is given by that the force of gravity is this gravitational constant, universal gravitational constant of about 6.7 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the first object times the mass of the second object in the system divided by the distance between them. So if you're near the Earth's surface, that simplifies down to m1g, or if you're near the Moon's surface or whatever. This approximation, Fg is about m1g, works when you're using that m2 is the mass of the Earth, so you're standing somewhere on the Earth, and r is approximately the radius of the Earth. If you're standing on the surface of the Earth, you are equal to the radius of the Earth away from the center of the Earth. If you get out here, though, somewhere out here, for example, sort of behind the Earth with respect to the Moon, you can still use the mass of the Earth here. You still have the same gravitational constant here, but this radius is no longer approximately equal to the radius of the Earth. It might be 2 or 3 or 5 or 100 times the radius of the Earth. And so in order to deal with that, you basically use the expression that the energy, the gravitational potential energy, is negative g m1 m2 over r. So this is how you get the gravitational energy more generally. And of course, you can in fact derive this expression using calculus. I'm not going to do that in this particular video, but the basic setup is that you no longer have a constant force, and so therefore you need to use the force over a small change in distance and then add up all of these little force times distances. Basically, in calculus terms, you take an integral. Let's do a few short examples here, though. How much work are we going to do if you are this woman who's trying to lift the television set all the way up to the fourth floor, which is about 12 meters above the ground? All right, this is the simple version. The ground is out here where this woman is standing, so that means that we are not lifting the object, into space or anything. It's not a space elevator or something like that. So the amount of work that's going to be done to lift this object is going to be the work done against gravity. So that should be the mass of the object times free fall acceleration times the change in height. And the change in height is 12 meters. And the mass is 30 kilograms. Of course, free fall acceleration is 9.8. So that means that the work done by gravity should be 30 kilograms times 9.8 meters per second squared times 12 meters. So that gives us a total work of 3,528 kilogram meters squared per second squared. And since we have two significant figures to work with, that basically means that the amount of work that is done here should be about 3,500 joules. So that is how much work this woman is having to do to lift this television set up to that fourth floor. Now note, of course, that she's lifting it to the bottom of the fourth floor. If she needed to lift it to the top, we'd also have to figure out this distance too. Presumably it's another 4 meters. Okay, our next example asks how much work is done by this man in carrying the television set up these 3 flights of stairs, assuming that the flight has a horizontal length of 10 meters. So this is 10 meters, and of course we're assuming that all of this is still true. So, 30 kilogram television set and all that. Okay, well, it turns out that this horizontal length right here is actually irrelevant to the problem because he's still working against gravity. So although in carrying this television he may be applying a force in this direction, the only thing that actually matters is the force that he applies in this direction, and that has to be the mass of the television set times the free fall acceleration. So the work done by the man is still work against gravity. One way of looking at that is that he has to apply some force in this direction, but the change in position is in the upward direction, so we'd use force times cosine of theta times the total distance delta r. And these two terms right here are going to combine in such a way that delta r is basically going to be from here to here. But if you were to sort of break that up into x's and y's, so here's x, here's y, the cosine of the angle in question is this angle right here, theta, because the force is actually upward, the gravity is actually in this direction, up, down direction. So the force he's applying is actually up, gravity's down. This is the angle between his displacement and the force. These two angles are basically equal. So this right here ends up being equal to y, or if you want, it's delta h. And we can basically do this for all three flights. And so the work done against gravity with this man who's walking up all these stairs is still going to be mg delta h. And as we found out in the last problem, that's about 3,500 joules. So he actually does the same amount of work in carrying this television up all these flights of stairs as she does, assuming that he's not losing energy due to friction, that kind of thing. If you have to take friction into account, then he's doing a different amount of work, but the net amount of work done to the television set is going to be the same as with this woman who lifts it up here and places it on this floor. Next question, how much energy is needed to lift a 1 kilogram object from the Earth to deep outer space? Now, this may seem like a very vague question. What do we mean by deep outer space? Okay, well, obviously, going from the Earth to the Moon is not really deep outer space. I mean, yeah, you went into space, but deep outer space usually means here's the Earth and you want to go infinitely far away. So we are basically going to go very far. Okay, so basically we are going to have some change in energy due to gravity, delta E sub g, and that is going to be E g initial, final minus E g initial. And E g in this case, we might as well just use our minus g m1 m2 over r, where m2 is mass of the Earth, and the mass of the Earth is usually given in most physics textbooks. For example, in the OpenStax textbook, you can find it in this nice table C3, which is solar system data in the appendix C, useful information. So the mass of the Earth, 5.9736 times 10 to the 24 kilograms. And while we're here, there's actually also the Earth's radius. So we have that mass of Earth, we'll just call this 5.98 times 10 to the 24 kilograms. Radius of the Earth, again, was given in that same table. We'll call it 6.38 times 10 to the 6th meters. So that gives us sufficient information to determine the initial condition. The final condition, this is initial. The final condition is radius goes to infinity. So if the radius is infinite, then this whole thing becomes 0. So that basically means that the change in energy is just going to be equal to G m1 me over re. So this is going to be what the change in potential energy for the entire system looks like. And so basically we can plug in these numbers. Recall that G is the universal gravitation constant, which has a value about 6.67 times 10 to the minus 11. So 6.67 times 10 to the minus 11, that's in Newton meters squared per kilogram. squared. So you basically end up needing to multiply your 1 kilogram object for mass m1. So this right here is mass m1 times this number times this number divided by this number. So let's have a look at that. This gives us a total change in energy then of about 6.25 times 10 to the 7 joules. So that's quite a bit of energy if you think about it, although again you could compare that to for example, how much energy does it take to heat water from say 0 degrees to 100 degrees C. And depending on how much water we're talking, this really may not be that much energy in comparison. Recall that water takes 4,186 joules to heat 1 kilogram by 1 degree Celsius. So, this is a couple orders of magnitude more than that energy for 1 kilogram to go from 0 to 100 degrees C. In other words, you eat a lot more energy than this every day when you're just eating your lunch or whatever. On the other hand, you can also see as a similar comparison, how much energy would this be equivalent to for an object which is moving? Well, a car has a mass of 500 kilograms, let's say. So how fast would the car need to be moving in order to have this energy? And the answer is actually about 500 meters per second. So in mechanical terms, this is actually quite a bit of energy, because very rare is the car, in fact I think it's never been invented, that can drive at 500 meters per second. That's 1,000 miles per hour. So it takes a lot of mechanical energy to lift even a relatively small object off of the Earth. Suddenly it makes sense as to why NASA will say stuff like, well, it costs so much money for every pound that we need to lift into outer space. NASA, for what it's worth, says that it's about $10,000 for 1 pound, basically to lift a 1 pound payload into Earth orbit. And that's let alone to get out of Earth orbit and to deep space. Moving on, I wanted to talk a little bit about that other type of potential energy that I wanted to look at in today's lecture. And that is the potential energy that's associated with a spring, elastic potential energy, if you will. So recall that the force of a spring depends upon how much the spring is stretched or compressed. This was, in fact, a point which was made in the 5th set of lectures, the second part of the 5th set of lectures, which was on forces and types of forces. So specifically, Hooke's law is the law that governs springs, and that was in the ideal form basically says that the spring constant times the displacement from equilibrium position gives the force of a spring, as long as you include a negative sign because it is a restoring force. And very commonly that's an experiment done in the lab. In fact, we do that in the lab in one of the earlier weeks in lab, in which you take a spring and you just keep adding some weight to it and measuring how much it stretches and adding some more weight and seeing how much it stretches, and eventually you get a straight line of basically how much weight you've added versus how much it's stretched. The slope of that line is actually your spring constant, etc. So of course, if you want to include a less ideal spring, you also end up needing to add to it a force that represents the initial tension in the spring. Basically, sometimes the spring is coiled tightly enough that you have to start adding force to it to try and stretch it, and it doesn't stretch until you hit a certain minimum amount of force. So here is the actual force that would be given by Hooke's law. And so the question is, how much work is going to be done by a stretched spring, or for that matter, a compressed spring, a spring that's been compressed beyond its equilibrium. So if the equilibrium position is here, the spring might be compressed back here, it may be stretched out here. According to Hooke's law, you still have a linear force versus displacement. So how much work would this do if we were to, for example, stretch it by delta x? Well, you may think that the answer is going to be given by some equation that looks like maybe ks times delta x squared plus this initial force times delta x. That may be the gut reaction. In other words, you may expect that the work done by the spring and therefore the potential energy stored in a spring to look something like this. Because again, recall that the work is always going to be force times the displacement, or the dot product between force and displacement, which would be force of the spring times the displacement of the spring times the cosine of this angle. And since the spring is always going to be displaced in the same direction as the force, this angle right here is actually 0 degrees, and hence the cosine is 1. So you might expect something like work is equal to ks delta x plus this initial tension times delta x, and hence to look like this expression. As it turns out, if you expect that, you end up being off by a little bit. And specifically in the case of an ideal spring where this initial tension is 0, you end up being off by a factor of 2. So the question that you may be asking, and especially those of you who are in the general physics class, is why does this not work? And the answer is for very much similar reasons to why we have to modify the equation that we use for the potential energy when we're dealing with gravity. The specific reason is that the force applied by a spring is not actually constant. Just like with gravity, when you get far away from the surface of the planet, the distance force becomes linear with distance in this case, as opposed to 1 over r in the case of gravity. But for both cases, that means that you don't have a constant force. In the case of the spring, it means that the force being applied is very small near the equilibrium point and gets larger as you get farther away. So your force versus stretch equation can have the form y equals mx plus b, and what that means is that we can use the average force of the spring rather than the instantaneous force at some given position. So recall that if you want to take an average force, you just take the force at one position, take the force at another, add them together, divide by 2. Okay, that means that if you wanted to use the work done by such a force, you could use the average force times the displacement times the cosine of the angle. And so the average force is going to look like force 1 plus force 2 times this displacement times cosine of theta. And so in the case of a spring, what that basically looks like is that this delta r is basically going to be change in the displacement from equilibrium. And so what that means is that the actual work done is going to look like 1/2 times the spring constant times the change in displacement squared. And then that can be minus the change in displacement. I've used a slightly different notation here than what I used earlier, and if this is a little confusing, it's because I'm trying to generalize more than what I was before. These diagrams show what happens if you take a displacement from equilibrium back to equilibrium, how much work is done in getting back to equilibrium. And so that's equivalent to putting 0 in for these delta x finals. And so then the delta x I used earlier is really the delta x initial. And so your equation looks like 1/2 times the spring constant times the initial displacement squared. And then that plus the tension force for the initial tension times that initial displacement. That's to get back to equilibrium. If you don't want to go back to equilibrium, then your equation gets slightly more complex. So this is basically how we can account for change in the change of position from equilibrium. So the process basically looks like that this 1/2 came in because we're taking an average force from the final position to the initial position. And of course this this term right here is basically that average force term. This term right here is the initial, and we have to multiply that then by the change in the amount that the spring is stretched or compressed by. So basically you introduce a factor of 1/2 as concerns the ideal spring, because in the ideal spring this term is 0, and in general you get 1/2 of this Hooke's law part of the spring force. All right, potential energy, again, is the potential for a force to do work. And in this case, the force is the force that the spring is supplying. So your spring potential energy, therefore, is going to be the maximum amount of work that you could get from whatever your spring has been stretched or compressed to until you get back to equilibrium. So again, that means that all those finals go to 0, because that's what happens when you're at equilibrium. And so that equation looks a little more simpler. It's 1/2 ks times delta x squared plus the initial tension times delta x. And again, if you have an ideal spring, this second term is 0, and so you're left with only the 1/2 ks delta x squared term. Most textbooks end up treating just the ideal spring, so it will just look like this part of the equation, and this one will be 0. But of course, if you're actually doing a spring in the lab, sometimes you have to include this latter term. Okay, in both of these cases, there's something that we should notice, and in particular, it should be easier to notice when looking at a spring, and that's that the potential energy for the ideal spring, at least, looks suspiciously like the area under a triangle might look. What do I mean by that? Well, here was the energy equation for the ideal spring. That doesn't look very much like a triangle energy, but we can rearrange this a little bit, right? This could be rearranged to be 1/2 times ks delta x times delta x. If we rearrange it in that way, then it's starting to look a little more like a triangle. Specifically, here is your base, here is your height, and then this is the 1/2. Area for a triangle is 1/2 base times height. And so let's look at that again with these energies in general. So again, the base is basically the distance along which the work is done. The height is the force which is doing the work. And it turns out that this works more generally. for those who have a bit of calculus background, the reason why may be a little bit obvious at this point. But even if you don't have a calculus background, even just using algebra, you can see how this might work in approximation. Consider some arbitrary force that varies with distance. Okay, work done has to be force times distance, but if it's varying, how do you get force times distance? Well, one way of doing it is to look at a little segment of the curve and basically do the force times the distance for that segment. And in a small segment, if you choose a small enough segment, then this force is basically constant during that particular segment. So it's got to be thinner than what these lines are drawn, or these rectangles, excuse me. But you can see that if we were to find the area of each one of these rectangles and add them together, that the area of any given rectangle looks like the distance that the object has moved. That's the base of the rectangle. And then the height looks like the value of the force applied, as it turns out, in the average, basically the middle of your rectangle. So as an approximation, the area under this curve might be approximated as area of each of these rectangles. If you add all those up, then you're basically adding up a bunch of little force times displacement. So you're adding up a bunch of little sections of work, so that should be equal to the total work. And this method of adding up rectangles like this is sort of the basis of integral calculus. It's called a Riemann sum. If you're doing algebra-based, then you can still at least find the area by drawing some rectangles and get a nice approximation. So I wanted to look at that in the context specifically of springs for right now, because again, a spring is actually quite easy to find the area under. Since the spring is linear, you're inevitably going to end up with something that looks like this. It's basically a triangle. And if you include a non-ideal spring where there's some initial tension, you actually end up with something that looks more or less like a triangle plus a rectangle. So let's go do a couple of these examples then. This first example is assuming we have a spring whose force function looks like this. In other words, force as a function of displacement from equilibrium. And we want to know how much work does it do as its displacement is changed from being stretched by 30 centimeters. So from 30 centimeters is actually right here, until it's compressed to 10 centimeters. That's right here. Okay, so there's a few ways that we can try to do this. One is that you can use your equation. The equation, again, work is going to be equal to change in energy. Notice that that is going to look like 1/2 times Ks times delta x final squared minus delta x initial squared. You can throw in a negative sign here if you'd like. The thing is that you'd have to get a value for Ks, and that is the slope of this line. So you could do that. There is enough data here to do that. However, it is, in this case, much more convenient to just simply do something like this. The work is going to be this area right here minus this other area right here. So if you find the area of these two triangles and subtract them from each other, you should get the total amount of work done by the spring. Okay, so how much work is that? Well, this right here, this height is roughly 20 newtons. So area number 1 is 1/2 times the height is 20 newtons, let's say, times the stretch was 30 centimeters, so 0.3 centimeters. Okay, so that's 10 times 0.3, that's basically 3 joules. Area number 2, so let's label this area 1, area 2. Area 2 looks like it is in the 10 newton height, so 10 newtons, and then this was 10 centimeters, so 0.1 meters. I erroneously marked this as centimeters. It is in fact meters up here. So half of 10 times 0.1 is 0.5 joules, and so the total work is going to be area 2 minus area 1 in this case. And so that is going to be 3 joules minus 0.5 joules, and so the total work is going to be approximately 2.5 joules. Okay. Of course, this is a bit of an approximation. You can see if you look closely that this is maybe not exactly at 20 when this is at 30 centimeters. This one maybe is not exactly at 10 when we're at 20 centimeters, but it's close enough to be within any reasonable margin of error for this graph at this scale. I also leave it as an exercise for the viewer to go and attempt to do this the other way, in large part just to show that finding this area is in fact a bit faster than trying to get an equation out of this. If you want to try it the other way, you've got to get the slope of this line and then use your equation. The negative sign in the displacement here sort of goes away because we're dealing with a displacement squared. So all minus signs go away, and so it's still going to end up being this squared minus this squared because it's a difference in the square of the displacements. So let's look at a slightly more difficult version of this. Not too much more difficult actually, but a little more difficult. It's not an ideal spring anymore. You can see where the equation method is going. In any case, what we want to know is suppose that this thing has some initial tension to be overcome. How much work do we have to do against the spring to get from equilibrium out to 25 centimeters longer than equilibrium? All right. Again, you could attempt to do this by using something like 1/2 ks times delta x final squared plus f0t times delta x final. Again, the delta x initial is 0. All right, but you'd have to get the value of this. That's going to actually come out of the slope. You'd have to get the value of this. That's actually coming out of the intercept. And then basically grind through the math. The other option, of course, is to find the area under the curve from the basically start of this thing over here to the end. So this area is not so bad to do because you can break up this object into one triangle and one rectangle. So here's your rectangle. The rectangle's height seems to be 20 newtons, and of course the base is 0.25 meters. The triangle also has a height of 20 newtons and also has a base of 25 centimeters or 0.25 meters. So the work done should be equal to 1/2 height triangle times base triangle plus height of rectangle times base of rectangle. And so that's going to be 1/2 times 20 newtons times 0.25 meters plus height of rectangle is 20 newtons times 0.25 meters. Okay, so that gives us a total work of 7.5 joules. So it's going to take 7.5 joules of work to get this spring stretched from here to here, and therefore also the potential energy is 7.5 joules. Okay, so let's now revisit the question of gravitational potential energy, and let's look in a few contexts. First context is suppose we stick near the Earth's surface. By the way, this graph here kind of shows us an example of what is meant by near the Earth's surface. This is basically the distance from the center of the Earth. So remember that the Earth's radius is about 6.38 times 10 to the 6 meters. So this point right here, this distance from the center of the Earth, also is the same thing as standing on the surface of the Earth. And as we go out to 6.42 times 10 to the 6th, we've added only 0.04 times 10 to the 6th. That's the same as 4 times 10 to the 4 meters. In other words, 40,000 meters above the Earth's surface, 40 kilometers up. This still looks like more or less the same force. This is a 1 kilogram object, so the force right at the surface of the Earth should be 9.80 newtons. And on this scale, that almost looks the same as 10 newtons. By the time we get out here to 40,000 meters above the surface of the Earth, we're still pretty close to 10 newtons. Okay, so in this range, the work done by gravity is going to just be linear with this distance. And that's why it is easier, in this case, to use just the height above the Earth. Because again, up to 40,000 meters, there really hasn't been much change in the force. And so you might as well just multiply this force times whatever distance you have, and notice that that actually looks like the area of a rectangle. So again, it's the area under this curve. And only if you go out to longer distances does this approximation start to break down. So, you can see how many zeros are in this distance. This right here is 2 million meters. And at the 2 million meter mark, you can see that, yes, indeed, the force of gravity has in fact decreased somewhat. We've gone from about 10 to about 5.5, let's say. If you have a graph like this, though, we all end up doing basically the same thing, and that is you draw rectangles and find the area of each rectangle. And on a scale like this, you can even just count these boxes, and remember that each box is basically 1 newton of force by 200,000 meters. And so each box here represents a newton times 200,000 meters, or in other words, 200,000 joules. So if you want to figure out how much energy it takes to lift some object from the Earth's surface to some given height away from the Earth's surface, you can just count how many boxes it takes to fill in under that curve and multiply by the number according to your scale, in this case 200,000. Given specific heights, you can also use that equation that says that the potential energy is G m1 m2 over r, or G times the mass of the object times the mass of the Earth divided by the radius. And that's how much potential energy it is. And so if you want to lift from one given height to another, you can also find the difference in potential energies for those. That would be basically using this equation and then taking a difference from position R1 to position R2. But again, if you're just given the curve like this, you can just as easily make rectangles or count boxes or whatever your favorite way of approximating this area is. All right, so that is it for today. I wanted to give credit where it's due for all the various graphics that I used. I guess I should also give credit to Pixar for using a picture of Buzz Lightyear earlier in this lecture. Thanks for watching, and I hope you enjoyed this video.